Hello and welcome to the third episode of the Explain It To Me podcast. I'm your first host, the Epic Gilgamesh, and joining me as usual is your other host, a meat-based android.
Hello.
Today we're going to be talking about light. For something so integral to how we humans perceive the world, light is not particularly well understood. There is, however, a good reason for this. Light is an incredibly complex topic, and to properly understand it, you really need to study the advanced physics yourself.
But don't
Don't worry, that's why we're here.
Yeah, don't do that.
We're here to help you to avoid that.
Yeah.
In this episode, we hope to explain some of the important concepts regarding light. Okay, so Mr. Android.
Oh, please call me Meat.
Okay, I don't really want to call you Meat.
Well, Android will do then.
Okay, Android. What is the starting point to understanding light?
I guess it's the electromagnetic spectrum. But how do we know about that? I mean...
Right, well, we see it, of course. You know,
yeah, we see it.
That's what we see. That's visible light, rainbows.
And, of course, people wanted to know, what is this thing that we're seeing? What is this phenomenon? What's the nature of it? How does it work? And one of the big questions was, is this action at a distance instantaneous? Does it have an infinite speed, or does it have just a very, very high speed? That's an important distinction, because it might not seem to make much difference whether it's infinity or very large, but it had some philosophical implications. And also, if action at a distance could happen instantaneously, that would lead to some sort of paradoxes and things that wouldn't work right. So people were trying to measure how fast the speed of light was. The early attempts were someone would get on a big tower or a hill and light a lantern and open the lantern, and then have their assistant on a tower or hill some miles away looking through a telescope, see the lantern, and then at the same time, as soon as they see your lantern, they light another lantern, and then you, with a stopwatch or something, try to time how long it takes for light to propagate. They found that light was much, much too fast for those methods to even remotely work. So they couldn't distinguish between very fast and instantaneous. But they got more sophisticated at it, and they had experiments with spinning wheels and slots in the wheel and sources of light and mirrors. And if you got the wheel spinning fast enough, the light would go through one slot, bounce off the mirror, and come back through the next slot in the wheel. And you could use the speed of the wheel to figure out how fast the light was going. And they were coming up with figures of something like 270 million meters per second, which is very, very fast, but not infinity.
So that's pretty close to the actual speed, right?
Yeah, which is
actual
around...
speed is 300 million meters per second, is that right?
Yeah, it's around that in a vacuum. So, I mean, that itself was an important result. But the curious thing was that at the same time, we had people investigating magnets and static electricity and wires and batteries and stuff like that. They had no interest whatsoever in light. But when James Clerk Maxwell put together all the equations for magnets and electricity and loops of wire and that sort of thing, he came up with the possibility, the theoretical possibility, that there could be waves of electric and magnetic fields that themselves would propagate at a speed which he calculated to be around 300 million meters per second. He calculated that based on the experimental results of magnets and electricity alone, and nothing whatsoever to do with light.
Isn't that how a lot of scientific advancements happen?
It can be. And he thought, this is too much of a coincidence to be a coincidence. This has to be connected. And so his hypothesis then was that light is itself an electromagnetic phenomena consisting of waves of electric and magnetic fields that bootstrap themselves through space, requiring no help from anything else. And then, it took a few decades, but it was eventually proven to be the case that you could use electricity and magnets to make an electromagnetic wave, and it would propagate at the speed of light, and it in every respects was light. And then eventually it was shown that the entire electromagnetic spectrum is all electromagnetic and is all light, and the visible light that we see.
So the radio is actually light. too,
Yeah,
just like what you see.
Your Wi-Fi, that's light. Your
Yeah.
microwave oven,
So I
that's
mean,
light.
this is
X-rays, that's light.
this is touched on briefly in high school science. That we all see the spectrum, but it's not very intuitive to think that your Wi-Fi is the same thing as what you're seeing, because your doors stop a light except for the cracks, but it won't stop Wi-Fi. I mean, you'll get weaker Wi-Fi, but it won't stop it.
Yeah, and
Like
X-rays, they can go right
it
through
would.
you.
Yeah. So what is the difference between these things?
The only difference is the wavelength, or in other words, the frequency at which it's oscillating. And based on what the wavelength is, an electromagnetic wave will interact differently with one material versus a different material. Visible light can go right through glass. Infrared light stops at glass, and you can't see through it if you have infrared eyes. Wi-Fi tends to go around corners and through thin walls, whereas visible light can't do that. It tends to go more in straighter lines, and it stops at most solid surfaces that we can see.
This is all related to how much energy it has, right? We see this, in basic in the visible spectrum. Red light is of lower energy than blue light.
Yeah, but it isn't always so clear cut. You can have a lower wavelength or a lower energy light that can go through something, and a slightly higher energy or shorter wavelength light would not be able to go through it. Look at the atmosphere, for example. You have infrared radiation that can go from the surface of the Earth out to space through air. But if you add a bit of water vapor or CO2 to the air, then suddenly the 100 miles of atmosphere becomes very opaque, and light of that same wavelength can't easily get through it. So it really is the specifics of what the material is and exactly what the wavelength of the light is that will tell you whether the light will be stopped, absorbed, reflected, or allowed to pass right through.
Right. So let's go back a few steps and talk about speed of light. So the key to this discovery was finding out that the hypothesized speed of light and the speed at which this guy had calculated electromagnetic waves to travel was the same. So this brings up an important question. Is c, or 300 million meters per second, the maximum possible speed because it's the speed at which light travels, or does light travel at c because that is what the maximum possible speed is?
Yeah, good question. Now, remember why they were measuring the speed of light, or trying to in the first place. They were worried about instantaneous action. Can any physical cause create an effect at a faster speed than the speed of light? Or can it do it at an infinite speed or instantaneously? Well, they found out in the case of light, the answer is no. It's the fastest thing they could think of, and even that wasn't instantaneous. So it turns out that the speed of light is the speed of light because that is the maximum possible speed. But why is it the maximum possible speed? Well, there you have to get into...
Do we know that?
Yeah, I can tell you why. I'll tell you why. It's because the speed of light is, in fact, the only possible speed ever. We're all going through space-time at the speed of light right now. But if you go through space a little bit more, you go through time a little bit less.
What is this space-time?
Well, there we have to go down the rabbit hole of general relativity. But basically, space is 3 dimensions and time is a 4th dimension. And you can go through space and time. You can go through either time, or you can go through space, or you can go through any one of the 3 dimensions of space. But no matter where you're going, you're always going to be going the speed of light. If we're just sitting here on our chairs, not going through space very fast, we're going through time at pretty close to the speed of light. But if we were a particle of light, for example, if you were a photon, you were going through space at the speed of light, you would not be going through time at all. That's why photons never get old. They never wear out.
That's what relativity is all about.
Right.
The closer you get to the speed of light, the slower time passes.
Yep.
We see this in science fiction all the time.
Yep. Yeah, so that might take a couple of more episodes to fully explain all the implications of relativity.
Yeah, we'll definitely have another episode to focus on relativity and this space-time thing.
Yeah. The really interesting thing about light is that light is sort of the confluence of both classical physics and modern physics. And in the case of modern physics, it's the confluence of both relativity and quantum mechanics, which don't always intersect.
So we've just been talking about how light relates to relativity.
Yeah.
So how does light relate to quantum mechanics?
Well, because in certain circumstances, light behaves as though it's made of little bullets called photons.
Like photons.
Yeah, photons.
Everyone knows about
we've
photons.
Mentioned them, yeah. So why does light behave like little bullets called photons when we already know that light is a wave of electromagnetic fields, as we discovered with Maxwell? Well, the reason is that energy can only go into and out of an electromagnetic field in little steps called quanta. And a photon is a quanta of energy, the minimum amount of energy that you can either add to or take away from an electromagnetic field.
So it's like an integer.
Yep, and when light is absorbed or produced, it is absorbed and produced in little chunks called photons, the energy of which depends on the wavelength. But basically, light behaves like a photon when being absorbed or emitted, and it behaves like a wave everywhere in between. So it travels like a wave, it diffracts and refracts, and you can have interference, constructive and destructive wave interference. You can have all those wave mechanics.
What is a wave? I mean, if you think of a wave in an ocean is just a big bundle of water particles moving in a certain way. So could it just be that light is a wave made up of photons?
It could be, except that the experiments don't bear that out. If you put a whole bunch of photons, as it were, together, you get emergent properties of wave, like destructive interference and so on. But even if you send in one photon at a time, over time, even without it interacting with other photons, over time, the same wave patterns will emerge in the results. So it really is as though it's traveling in the form of a wave, but it's being produced and absorbed in the form of a particle or a discrete chunk of energy. So an ocean wave...
Maybe it's stretching out, like the photon particle that stops being a little ball and starts becoming a long wave-shaped thingy.
Well, except that it never was a little ball in the first place. I mean, most physicists won't necessarily think about it in this way, but I think that photons don't actually exist. They're just these steps or the chunks by which energy goes into and out of the electromagnetic field. So light isn't actually traveling through space in the form of little bullets of energy called photons. They're traveling through space in the form of a wave, and what that means is an electric field can be rising, and while it's rising, it can generate a magnetic field. And a magnetic field, when it's changing in time, can generate an electric field, which in turn generates a magnetic field, which in turn generates another electric field. And so these fields are out of phase slightly, and their rate of change creates the next field in the chain, and so you get a never-ending self-propagating chain of sine or cosine waves of electromagnetic fields. And so once you get it started, it propagates itself all the way forever until the energy gets absorbed.
I understood very little of that last bit, but so what you're saying is light is two guys making a human pyramid where the guy on the bottom keeps climbing onto the guy on the top, and they're slowly getting taller?
Well, you think of them more of sort of slowly walking themselves along the ground, where one gets in front of the other and he pulls the other in front of him and he pulls the other in front of him and so on, and they self-propagate. Electricity and magnetisms are manifestations of the same thing, basically, in nature, but when taken together, they can create a self-sustaining wave that can carry energy and momentum through space at the speed of light, because that's the fastest speed that any physical effect can have an effect.
Right, that brings me to another question. So we all know that light carries and imparts energy. You stand in the sun, if you're warm, that warmth is energy coming from the light. But at the same time, light is reflecting off of you. That's how other people can see you. So how does that work? If, these photons or wavelengths are hitting you and bouncing off and imparting energy, how do they keep going at the speed of light? Or is all light that you see actually going slower than the speed of light because it's already bounced off of a million different things?
Well, it depends on if it actually bounces off of you or if it gets absorbed or scattered. If you're a mirror, then light is probably going to just bounce right off of you, and the mirror is never going to get hot. But if you are something that isn't a mirror, not reflective, most of the photons will be absorbed into you and then heat you up. And some of them will reflect off of your surface, and some of them will scatter off of the surface. And during scattering, sometimes the wavelength of the light can be slightly altered. But most of the time, it's a filtering effect where certain wavelengths will scatter, and so you see that color, and other wavelengths will be absorbed, and so you don't see that color. So you shine white light onto something, say that's red, the blue light gets absorbed, the red light gets reflected, and what you see is the color red.
Right, so that's what plants do. They have green leaves, so they reflect the green light and absorb the others for use in photosynthesis.
Yeah, they need that blue light. That's what they need.
Yeah, because as mentioned previously, blue, different wavelengths have different energy, and blue is higher energy than red.
That's right.
So I've always wondered why we don't see, why are all plants not red?
Well, the interesting thing about plants and flowers is that most of their interesting colors aren't even in the visible spectrum. They're in the ultraviolet spectrum where insects can see them. So insects can see a whole different world of flowers than we see. They see very interesting patterns and colors that we're just not seeing. And so that's really where plants are trying to do, is they're trying to attract insects, and so they're playing to the crowd.
Right. Now, I wonder, do you know if anyone's ever used a infrared ultraviolet camera to look at those sorts of things? See what they actually look like?
Yeah, you can get an ultraviolet camera, and there's photographs of flowers under UV light. Yeah, it's really interesting. And I've got an infrared camera, a thermal camera that attaches to my cell phone. It's really fun to go around looking at everything's thermal spectrum. You can see things that are warm, things that are cold, based on what infrared light they're radiating. It's a lot of fun.
We've mostly wrapped up the meat of the episode, but let's keep talking about this for a little while. So why is it that the infrared is what carries heat? Why is everything, thermal cameras in the infrared?
The interesting thing is that ultraviolet light, the photons actually carry more energy than infrared photons do, but it's the question of how to produce light. And the way you produce light is basically by shaking something that has an electric charge on it, like, say, an electron or an atom that has electrons in it. And if you shake them really hard, they produce wavelengths of light, and the frequency of which is how fast they were being shaken. So if you shake something really fast...
I just had an image of a bully shaking guy and money flying, and that money is light.
Right, and radiation is coming off it. Right. So if you shake things at a low temperature, you shake them slowly and you get infrared light. If you shake things at a high temperature, you shake them really quickly and you get shorter wavelengths of light, such as yellow and blue. The thing is, to get something to radiate mostly in the yellow color range, you have to get it up to around 5,000 degrees, like the surface of the sun. To get something to radiate
or fire
at a low, dull red, you need to get it up to 1,600 degrees Fahrenheit, where you see metal starting to glow red hot. But to get something to radiate deep in the infrared, you don't have to heat it up much at all. You can breathe on it, and it will start radiating slight amounts of very low wavelength infrared light. So that's why we can see heat really well if we look in the infrared spectrum.
So it's because infrared light is so cheap.
Easy to make,
basically.
Yeah, easy to make.
Yeah, very, very little energy requirement. So lower energy, as light you might find in a human body, makes it without much trouble.
Yeah.
Whereas if you wanted to look for the ultraviolet, you'd only see the really, really hot things.
Yeah, like the hottest things in the universe are the matter that's being sucked into a black hole, and they emit X-rays, and because they're just so hot. And so the hotter something is, the shorter the wavelength is that's being emitted. And
wait, so X-rays are the hottest thing in the universe. What have I been getting shot into my bones all these years?
Yeah, well, very short wavelength light. Of course, at a low intensity, you get an image off of it. It's ionizing radiation, and it can certainly make chemical changes to the cells in your body. So, be careful about that. But basically, yeah, very
Wear
short.
the lead cup.
Yeah, wear the lead apron, that's for sure. But X-rays for that are produced in a different way than by creating something super hot. They're created by making a beam of electrons, then slamming that beam into a big slug of copper, and they come to a stop really abruptly. That creates the X-rays.
Thank you for listening to the Explain It To Me podcast, episode 3. We hope you have enjoyed it and look forward to making the next episode. We haven't decided on a topic yet, so feel free to contact us by email at explainittous@gmail.com, via Twitter at explainittous, or on our Facebook page with any comments, requests, or recommendations. Until next time, keep thinking.